Hi, Narguess.
Hi, Peter.
Thank you for accepting my invitation to take number two in the podcast on everyday metallurgy.
That's a great honor and pleasure of mine to be at your podcast, Everyday Metallurgy. And I'm very happy that the previous one um, got the attention of people, and now you came back with more questions. That's my
Yes,
honor.
because what happened last time was that uh, I was so amazed with the answers you gave that I simply forgot some of my questions, and uh, some other questions appeared when I came home and tried to take in what I had just learned. And then, oh, I forgot to ask about this and that. So therefore, I call you again and ask if we could take another one. Uh,
That's wonderful. Yeah.
yeah. So what we talked about was materials for fusion reactors. So it's the energy source of the future. Uh, but when I came home, I was just a little uncertain about what are these reactions that occur in the system. We talk about the Iter reactor, and there was a lot about deuterium and tritium and helium and lithium, and I got mixed up in how it works. So therefore,
Yeah, that's right.
if you could share a little about what are the reactions that really occurs on atomic scale.
Sure. First of all, I want to say hello to all the audience and the people who see or hear us. And thank you for inviting me again. I have to, in the beginning, say that there are many people, many scientists out there who are more qualified than me to answer these questions. And the fusion science has been booming really well over the
Mm.
past decades, and there are many people who are getting interested newly, and we have a lot of students who have questions. And I hope that this podcast or this episode can inspire some of them to follow up fusion as their own
Mm.
career path, maybe, or a study branch or a study field. Let's take it from where we left it last time. I agree. I think we talked about fusion, general information, what is fusion, and what's going
Mm.
on in the world about that. And we talked about the ITER machine. Um, in order to have like a review and then go on with your questions, I would like to say that there is a major difference between fission and fusion. When we look at the periodic table with respect to the nucleon binding energy, the lighter atoms yield energy by fusing together, like
Mm.
hydrogen isotopes that are the main source of fusion reaction. Up to iron, the lighter atoms, by fusing together, theoretically can yield energy because the combination, the nuclei of the fused atoms is usually lighter than the sum of the individual ones. And that amount of mass that is not appearing in the sum of the combination converted to energy or yield as the fusion energy. But one should know that in order to have the fusion energy, you have to penetrate the Coulomb barrier by the aid of tunneling, and that requires extremely high temperature. We are talking about millions of kelvins.
Mm.
And then it will yield in energetic neutrons, and then we have to harvest the energy by controlling those energetic neutron particles. And up from iron, the heavier atoms, they can yield energy by fission and by splitting into lighter atoms.
Mm.
And then, like uranium is a very famous example of that. That's the
Mm.
fission reaction. And if I may share, I want to show the fusion reaction.
Yeah. Yeah.
Yeah, this is the deuterium fusion, the deuterium tritium fusion reaction in the black picture, and there are four different possibilities for fusion reaction using the isotopes of hydrogen. You can use deuterium, 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 tritium, and deuterium, helium for yielding the fusion energy. But the important thing is that one of the most feasible reactions that we are thinking about it and the fusion scenarios now is centered around this reaction is deuterium-tritium reaction. We talked about it in the previous episode, and we said that, okay, deuterium is abundant, but tritium is not, and we have to think about the tritium breeding within the system. Then we can have a sustainable chain of reaction when the tritium can be consumed and breed, and then consumed and breed, and then 17.59 mega electron volt of energy, which is helium particle, and a neutron with 14.1 mega electron volt energy is the yield of the energy that we have.
And where does the tritium come from?
The tritium first, if you're talking about the very beginning, we should have some tritium ready, and then we use these gases as, and then we insert them inside the plasma. And then we heat up the plasma and confine it long enough in the very high temperature that is enough for the nuclei of deuterium and tritium to fuse together. But then when the tritium is being consumed, we have to think about producing tritium or breeding tritium. The energetic neutrons that are created here in this reaction, in another process, in a tokamak scenario, are hitting the breeding blanket, where it consists of some lithium, and then the lithium in the can yield some tritium after the energetic neutron hit that. So that's how we create or we breed the tritium for the system, and then it goes back to the tokamak, and then the reaction will continue.
Yeah, so it's an in situ manufacturing of the tritium.
Exactly.
That was something I didn't understand last time.
Yes, that's in situ, sort of.
Yeah. So when you have this blanket of lithium that is consumed during the process, how thick a layer is it, and do you know if they have calculated a lifetime over the production? I know Iter is just a test facility, but when going into next generation and going industrial, either you have to be able to have enough for the lifetime of the entire machine, or you need to be able to replace it. Do you know if there's been any calculations based on that?
There are calculations based on that, but the reality is unknown because we have to wait for the Iter to operate, and then the next generation of Iter, which is demo reactor. And then in reality, when you have those complex situation in action, in practice, energetic neutrons, very high temperature gradient behind the breathing blanket and so on, and you see the whole complexity together working, then you can understand, okay, now we can have the information whether the lithium is the time for replace it, or we can still use it for another couple of years. This is something that the answer will come with it when the Iter starts operating.
Yeah, because it must be eating from the surface and be thinner and thinner layer.
Yeah, Peter, I know that as a metallurgist, you very much are sensitive about being eroded and corroded and eating out of the metal.
Yes, exactly.
That's a very valid concern.
Yeah. Then we also talked about what you call the primary war,
Yes.
The first wall that was made in tungsten.
Yeah.
And you said it was alloyed with some micro elements that made it not degrade in these very aggressive radiation environment. Um, you said that this alloy was made in a special way by a few companies. Can you elaborate a little on the alloy itself?
Yeah, I understand that the previous episode raised some curiosity because I didn't name the companies. There are two Japanese and Chinese companies basically that produce fusion grade tungsten. The Japanese one is ALMT and the Chinese one is AT&M, Advanced Technology and Materials.
Mhm.
This is the abbreviation AT&M for that company. They produce tungsten for fusion machines, and as far as I know, they do not reveal the alloying element, the trace elements that they use.
Mm.
And we don't know about the production line that much in these two companies, how they produce these slabs of tungsten. But from my own firsthand experience as I worked with these materials, I would say that they are very well resistant to grain growth when they are subjected to extensive high heat flux pulses, which is going to be the case for the tokamak scenario and especially for the divertor part.
Mm.
I will explain shortly what is the divertor, but the first wall and the divertor, they are in-vessel components that are all inside the tokamak in the vacuum and before the breathing blanket. So they are basically the first element that is in connection with plasma, in contact with plasma.
Mm.
And these tungstens are going to receive a lot of energetic particles and neutrons and a lot of heat. And behind them, there is a coolant, so a heat gradient also is there. We have been testing the divertor mock-ups, and mock-ups are the prototypes that are similar to what is going to be in the reality.
Mhm.
And these tungstens were reacting very well to high heat fluxes as high as 30 megawatts per square meter. And for 500, 1,000 cycles, we couldn't see severe degradation or grain growth or abnormal recrystallization. So as a metallurgist, you would imagine that when you don't have the grain growth or big grains after such heat fluxes, you are safe to say that your material is not degraded. So that was my experience with these two companies' materials.
Mm-hmm.
And I have been working in Max Planck Institute for Plasma Physics as a researcher back then in 2021 and 2020. And one of the researchers that I have done there was working on these materials, and the results yielded very good resistance to heat fluxes. And I have published these results I want to show. So this is basically the paper that is reporting on the results that me and my colleagues at Max Planck Institute were working on it. The microstructural evolution of tungsten under thermal loads, a comparative study between cyclic heat flux loading and isochronous furnace heating. So that was the study that we did, and on both of these tungsten grades, I can show you here better. You can see if this is from AT&M company, and this one is from ALMT from Japan.
Mm-hmm.
And as received, and then the same sample after exposed to 500 cycles of 20 megawatt per square meter at the temperature of 1,500 degrees C filled, because there is a coolant water in here. And this is the real shape of the mock-up for the divertor. Okay. And here you have the coolant water which could be a hot water or cold water. And then this is the copper field, the copper pipe, and here are the tungsten parts. And then I was doing this experiment somewhere here, cutting from here and looking at that. And what we have noticed that in these temperature fields, different grain growth and recrystallization regimes happens. And when we looked at the two company provider, we noticed that there is not a big difference. And then they can yield very good results in very high temperatures at several high heat flux pulses of experiments. That was one of my first-hand experiences with these two companies.
Then the big question comes, how do you build up test facility where you can test at this high energy impact and at this temperature?
Okay, that's a very good question. Actually, the simple answer to your question, Peter, is that there is no facility today that can test the material similar to what happens in the fusion machine. We don't have, because simply we don't have that energetic neutron created, because only it is created when fusion happens. Whatever we do or whatever reaction we can manage to have yields with lower energetic neutrons, not as high as 14.1 mega electron volt. But the good news is that there is a facility being built and constructed in Japan and in South Spain, Granada, IFMIF DONES, that's the name of the facility. And IFMIF is International Facility Irradiation Nucleation Test Facility, which is going and promised to be able to test the material with the real energetic neutron situation as it happens during the fusion. And how it works, then I have to again share my screen to show how it works. Let me find this facility that you see here, IFMIF and DONES. Like I said, the program started by Japanese. They wanted to build up this facility in Rokasha, in a city in Japan, and then they test the material for fusion. But then the European Union also were working on fusion machines for a long time. They decided that to have a mutual act on that. Now DONES in Granada in Spain is a combined facility with IFMIF to address that need for testing the material in the real fusion condition. So they have a roadmap. They define that when the facility is validated and when the concept is being practiced and how they want to construct it. And the timeline shows that up to 2060, we can expect that they are still developing and testing the material for the commercialized fusion machines. But what is the basic of this machine? As you can see here, the basic of this machine shows that I want to bring it down, that you see the whole page here. So in very short explanation, there are two deuterium accelerators that they will converge, and they both are in continuous wave mode at 40 mega electron volt, impacting with a beam footprint of 200 millimeter by 50 millimeter at a 15 meter per second lithium flow, 250 degrees C. Then the lithium screen has twofold function. First, to absorb the 2.2 by 5 megawatt beam power, and second, to react with the deuterium to generate neutron flux. Then the magic happens and you have the neutron flux that you need for 20 displacement per atom per year, which is really big. And that's what basically the first wall materials would experience, or the blanket module would experience in the tokamak scenario, 20 displacement per atom per year. And you can put your samples in this chamber and choose what kind of neutron flux you want to create to test your material. That's how they are going to test it in a real condition.
Okay. What will happen if I just took a standard tungsten material? Would it be a single crystal, or would it degrade, or what would happen compared to the doped alloy you showed before?
I think this, I don't have a complete answer because, again, I have never had any report on irradiating the tungsten with this high neutron flux. It doesn't exist yet. We have done it with 6 mega electron volt, which was the iron facilitated neutron by iron reaction. And then the result was that tungsten is pretty fair enough to resist with this 6 mega electron volt neutron beam. But more than that, I haven't seen any report.
Okay.
So it's a big unknown, and we are all excited to know. There are simulations, of course, but in reality, we should someday reach to the point that we can match and validate our simulation with the experiment.
Yeah. When we talk about the Iter, we are often saying that it is the process of the future, and a lot of delays. It should have been running in 2015, or it should be running in 2025 or in 2030, but it's postponed, and it seems to be the technology of the future, of the internal future. But what is your perspective on that? Many people, they see the Iter as just a prototype where we prepare for building the real one. But what is the real perspective? There must also be some learning that could be spun off to other technologies.
Definitely, Iter is a learning facility. We had JET, which is the Joint European Torus, and it's in Culham in the United Kingdom, and it served the fusion community for 40 years now, and people have learned a lot. And the first deuterium-tritium reaction ever on this planet successfully yielded fusion in that machine. So we have learned a lot from JET, and now that Iter is coming to succeed or to be the next generation, which is in much bigger scale. And then we have this all the magnet and magnetic confinement fusion in practice with Iter for the first time. And we are going to test the materials. We are going to learn about the resistance of the materials. We are going to learn about the stability of the plasma, how we keep the plasma hot, how we get rid of the plasma cooling by particles running around. So this is a very important stepping stone toward reaching the commercialization of the tokamak scenario. If we want to one day soon, let's say in 10 years, say that we have a solution for commercializing the tokamak scenario, without any doubt, Iter is going to be the stepping stone for that, and demo after that. And then when we have understood the flaws and mistakes and how to solve them, that's why the Iter is being delayed, because some of the components are being built and are transferred to Cadarache from different cities around the world, from South Korea, from China, from Russia, from India. But when they put it in place, because it's the first kind of this machine at all, they find there are some mismatches or miscalculations, and then they have to delay that phase and then go for a solution and then correct it in a way. So I would say that this trials and errors are very, very natural for such a huge scale energy machine. And that's going to be a very valuable learning facility for the tokamak scenario. And yes, that's why. But the good news is that by now is not anymore going to delay, and we know some sharp timelines. And by 2030, we have the first ignition. So hopefully, if we survive 5 years, we see that.
Yeah, we better do that. Your focus has been on material development of the tungsten components inside the vessel, but there are also other materials. Are they fully developed, or are there still material development going on within fusion reaction?
This is a very ongoing process and continuously developing, rapidly developing field. There are 109 distinguished materials and components that should be developed for the tokamak scenario and Iter itself, which didn't exist in the market before. And so these materials are being developed exclusively for this tokamak scenario. And tungsten is one of them. Divertor machine in vessel, they all come to, as we talked, experience a complex situation of high temperature gradient and energetic neutron particle incidence and displacement per atom per year, along with the thermomechanical tensions and a lot of thermochemical reactions that they have to resist. So degradation of these materials is going to be understood and studied better when we have the fusion reaction in reality happening or in one of the test facilities. But from the simulation, from our backup knowledge, from our literature, what we have learned so far from the degradation of the materials, I would say that this is a very interesting and rapidly developing field of science, fusion materials.
Yeah. Do you know if there? I remember when the Americans went to the moon with the Apollo project. They also were in the kind of same situation where they lacked technology, they lacked materials that could enable it, and a lot of that made a spin-off into our daily life. Do you also know if there are some of these materials that has been developed or are to be developed that will influence other areas than fusion?
Yeah, I think there are many of these materials that are being developed, and some of them are very useful for fission reactors as well, because if they can withstand the complex situation at a fusion reactor, they can definitely withstand the fission reactor situation. One of the very famous steel components that has been developed for the fusion reactor is called reduced activation ferritic martensitic steel, and that is reduced activation because obviously we don't need any radioactive things messing up around the other things. So iron, along with chromium, if I'm not wrong, vanadium, titanium, tungsten itself, silicon, and carbon, they are the tracing elements in this reduced activation ferritic martensitic steel. That's basically for structural parts of the tokamak machine. But also, like I said, because they are reduced activated, they are very strong, they have a very good temperature window to resist the complex situation. They are very useful for spacecraft applications, for another harsh condition application service like the fission reactors. I remember when I started learning about fusion back in 2014, still the carbon was a very popular material for the first wall. Even the vest, which is the new name for this tokamak in France, now the name is vest because they changed the wall from carbon to tungsten, and then W in the beginning now represents the tungsten. So they made the whole machine with a carbon first wall made of carbon, and then they thought that, oh, it's not a good idea because volatile hydrocarbon compounds are being produced here and they messing up the plasma. So they thought that carbon should be at any cost avoided. So they changed the whole wall and then they replaced it with tungsten. Things happens and then knowledge advances.
Yeah. Wow. Then if you go to Google and look for a fusion reaction, I have also seen other technologies that could be the future of fusion. Is there anything behind it? Do you know anything about these other technologies and how do they work?
Oh yeah, that's a good question. There are, let's say, maybe 5 or 6 different scenarios that are strongly being followed up in US and Europe and Asia. And tokamak scenario that we have so far talked about, which is what Iter machine, demo machine are following, is only one of them. And that's based on confinement of plasma with huge magnetic fields, and then keeping the plasma for sufficiently enough time in that hot temperature, in that stable status that the fusion can happen. But then that needs a lot of other technologies to be developed to help and back up that physics of fusion. One of them is superconducting magnets. You need to reach to the point, one of the technological breakthroughs that should happen for commercialization of fusion, to have a yield bigger than 1 or to have the output bigger than 1, is that you should have superconducting magnets that work in higher temperatures, which do not exist now.
Yeah.
And that's one of the reasons that fusion couldn't yield bigger than 1 yet, because still you need a lot of power to cool down the superconducting magnets that
just
you are
to run
using.
the magnets.
Exactly.
Yeah.
But one of the scenarios that is actually bypassing these superconducting magnets is called Z-pinch. And Z-pinch, the definition or the physics of the Z-pinch is that in a fusion power research, it's a type of plasma confinement system that uses an electric current in the plasma to generate a magnetic field. And that magnetic field is very, very powerful, that compresses the matter. And this system originally is referred to as pinch or beta Z pinch, but the main reason for that is the vertical direction of the current that is in the Z direction and goes through the plasma and then creates that huge magnet is in the Z direction. So any machine that have this configuration is correctly named as Z pinch. So they are saying that, or they are claiming that we want to get rid of these huge magnets and magnetic field producing superconducting magnets. And just by having a current through the plasma, we produce that magnetic field and then condense the matter. That's one scenario. America is very much following that up. There are a few good startups that have a big chunk of money from the government and private investors that they are following up this scenario. And if that happens, Peter, this is a very compact machine that can be inserted in one of the spacecrafts and produces the energy like an eternal clean energy that let us go to the interstellar spaces and discover.
That's the one you have behind you.
Yes.
Yeah.
That's the one I have behind me. That's the ambition.
Mm-hmm.
This is one scenario called Z-pinch. The other famous scenario is inertial confinement fusion. Here we are not talking about magnetic confinement, but rather we are having a small plate that we have injected deuterium and tritium fuel in it, very dense, and now we are going to converge a very high power laser beams on these plates. Then what happens is that the nuclear fusion reaction happens when this energy is ablating the plate, and the explosion happens outward, and some waves of energy is happening inside the target, which is enough for the fusion to happen. The shock waves that travel through the target, they produce a force that is enough. They compress and heat the fuel sufficiently enough that the fusion happens. So this is another scenario. A National Ignition Facility in Los Alamos in USA have had reported a breakthrough for that. So they said that they had a breakthrough 2 years ago. That's one of the most successful scenarios so far, better than tokamak even. Yeah. And in Germany, there is one company that I'm aware of, Marvel Fusion. They got a very good money and fund from the government to commercialize this scenario. Mm-hmm. And there is another scenario which is very similar to tokamak and is called a stellarator scenario. This is this donut-shaped plasma holder with magnets. Still, the basics is confining the plasma through the magnets. But what is the difference of a stellarator and a tokamak? Stellarators are better in keeping plasma stable, whereas tokamaks are better in keeping it hot. But they are promising for commercializing fusion in 6 years, and that's one of the promises of a new startup in Germany called Proxima Fusion. They are a spin out from Max Planck Institute for Plasma Physics, and they have had very good connections, collaborations, funding opportunities, and granted funds to revolutionize the energy system and commercialize the fusion within 6 to 10 years, hopefully.
Wow, that's pretty fast.
Yes, and I would say that I don't think they are bluffing because the amount of knowledge that have been accumulated so far and advanced, along with the technological breakthroughs and engineering successful developments, it's gonna be reality that we see the fusion to hit the grid and lit up our houses in our lifetime. And I'm very hopeful for that.
Yeah. So all these processes, are they using the same feedstock, the deuterium and tritium, as with the tokamak, or are there any different there?
The Z-pinch, the inertial confinement fusion, and also the tokamak scenario and a stellarator, 4 of them are using deuterium tritium as fuel. Yes.
Okay. And do they also use lithium as breeding material for feeding in tritium?
This is that I'm sure about the tokamak. Yes, that's what the tokamak scenario is using for breeding the tritium as a sustainable chain of reaction.
Yeah. But the other, how do they feed? If you have a laser and a plate where it hits, you put your feedstock in there, and then you heat it up, and it kind of explodes. It's like a small scale atomic bomb, isn't it?
That's true.
Yeah. Ooh. So how do we put in a new one? How you have to add a new every, I don't know how often.
I think you are asking about different plates. If one plate is exploded and yields energy, that's it. It's totally gone. And then another plate and another, because now the challenge for this scenario is not the plate, the core and the shell, and how to have that condensed matter in one core and shell structure, like a small plate with very condensed matter in it, is easy to make. But rather the challenge is the laser beam and focusing that energy to the right amount of energy to the plate to explode it and then to create that wave shock, which can provide the heat and pressure enough for the fusion to happen. That's the challenging part. There was a joke used to say that 10 football fields of laser beams are needed to converge and provide that heat that is needed.
Yeah.
But with
now
the,
it's only
with the
2.
advances in the laser technology now, we don't need 10 football fields.
Okay, we can do it with 2 or less.
At least 1.
Yeah. It's really crazy. So within 6 years, we expect to have fusion happening. Will that be locally, or will it be country-size energy supplies?
I think in the beginning, when we have Iter in operation and then demo, and then we learn from the mistakes and how to improve, I think the first commercialization, whatever scenario comes first as the commercialized fusion machine, I think first the members who have been working on it will benefit from that, and then they will sell it to other countries as selling the technology. I think so. That's what I imagine.
Yeah.
But there shouldn't be more expensive than fossil fuel, because now we have suffered the energy crisis after the Ukrainian war in Europe. And you have noticed that when the Nord Stream was destroyed, we have jump in prices, and that would affect everything. I would assume that even if the technology in the beginning is expensive, because the energy is eternal and it doesn't need an expensive source to fill in it, then you are one time paying for the machine elements, and then you learn how to assemble it. That would be the lifetime investment that you do in your country or your city. It's gonna make the life easier, I would say. So it shouldn't be something that we deprive some nations and we privilege some, but it had the mission to make the life easier.
Wow, thank you very much. I think that is a perfect end of our second episode to make life easier for everybody.
Yeah, that's the purpose, and we are very hopeful, and that's why I myself wanted to spend my career on it. That this is a big mission that I wanted to contribute in it, and I hope that within 6 years we talk again, Peter, and we talk about how Denmark is benefiting from this eternal energy.
That would be fantastic.
Thank you very much, Peter, for having me.
I really enjoyed it.
Me too.
Yeah. See you.
Bye-bye.
Bye.